Welcome. In this video, we're going to take a closer look at experimental error and how you propagate that and discuss it, particularly in your internal assessment. So your experimental error is the difference between the recorded value, or your value that you came up with, your calculated value, and an accepted literature value. And that's your experimental error. And that can be due to random or systematic errors. And again, random error is acceptable, and in fact, it's unavoidable. It has to do with reading your instruments or the precision of your instruments, and it has an equal chance of making your results high or low. But systematic error is the result of a flawed procedure, and it would be assumed that you would determine you have some systematic error and then correct it in the planning stage before you collect and keep data for your calculations and your analysis. Random error is also known as uncertainty, and again, it's caused by the readability and the precision of the instruments used. It's also caused by collecting insufficient data. That's why a minimum of 3 trials for 5 different data points is considered sufficient. Although, ideally you'd want far more than 3 trials. 3 trials is simply a minimum. It's also caused by the observer needing to estimate things like the last digit on analog equipment, or determining when a color change has occurred for a titration, or a reaction rate when using a stopwatch. All those things contribute to random error or your uncertainty. Because it has an equal chance of being high or low, it will be minimized or balanced by running many trials. It will average out. So if the same experimenter runs the experiment over and over with the same results, that's considered a repeatable experiment. But what we really want is that another experimenter can come in and run your experiment and get the same results. That then makes it reproducible. So all experiments need to be first repeatable and then reproducible before others are going to accept your data. Systematic error, again, is caused by poor design or procedure, and they will skew your data high or low. And these are not going to be reduced by running multiple trials. So if you can eliminate systematic error, you need to, and if you can't eliminate it, you need to account for it. So some examples would be overshooting the endpoint of a titration. When you have equal amounts of hydrogen and hydroxide ions in your solution, it is almost impossible to know that you're waiting for a color change, which means you've just gone beyond the endpoint. Heat loss in a calorimeter or any exothermic reaction. Those are systematic errors that you do your best to control. There's some things we can do to minimize it. Other systematic errors, like reading the top instead of the bottom of a meniscus, that's just flawed procedure. The smaller the systematic error, results in greater accuracy. So systematic error impacts you getting the expected or correct result. Smaller random error results in greater precision, which is your repeatability. So systematic error feeds into your accuracy and how much experimental error you're going to have, whereas random error determines the precision or repeatability of your experiment. Remember, accuracy is being close to your target or expected value, whereas precision is getting consistent results. And of course, we want both. Absolute uncertainty is a numeric value for your uncertainty, not a percentage. And we often convert uncertainties to percentages when we're propagating it or carrying it forward. But it's the actual uncertainty associated with the measurement, and we list it as a plus or minus after the measurement because, again, it could influence our results either high or low. So you can add or subtract the absolute uncertainty and get an acceptable range for your data. Percent error is not the same as percent uncertainty. Percent error is looking at your experimental error and expressing it as a percentage of the difference between your expected and your actual results. And what you're hoping is that your percent error won't exceed your percent uncertainty. So how do you propagate uncertainty? Well, if the initial reading on a burette is 15.05 milliliters and the final reading is 37.20 milliliters, we can assume the uncertainty for each measurement is half of that final digit, or plus or minus 0.05 milliliters. Because this is going to be analog equipment. So express the change in volume with the uncertainty. When I go ahead and take 37.20 and I subtract the 15.05, I get a difference of 22.15. And now my uncertainty is plus or minus 0.10 because I have to add the uncertainty associated with each measurement, which was 0.05. And I express this as 0.10, not just 0.1, because I need to hang on to my sig figs. What is the absolute uncertainty for the perimeter of a box with a length of 40.0 plus or minus 0.5 millimeters and a width of 20.0 plus or minus 0.5 millimeters? So to come up with the absolute uncertainty for this perimeter, I'm going to need to just add up 2 times 40, or 40 plus 40 actually is what I'm doing. So I've got 40.0 plus 40.0 plus 20.0 plus 20.0. And each of these values has an associated uncertainty of plus or minus 0.5 millimeters. So I can go ahead and add up my values and get my total perimeter of 120 and 0.0, keeping my sig figs. And then my plus or minus, my 0.5, I just add it up 4 times and get 2.0 as my absolute uncertainty. But doing the area, it's going to get a little more complicated because now I'm going to multiply the 40 times the 20 to get the area, so I get 800.0. But now calculating my uncertainty, I have to first know what is the percent uncertainty of 0.5 over 40 times 100%. So when I do that, I find that that's a percentage of 1.25%. And then I do the same thing with 0.5 over 20, and I find that's a 2.5%. So this is a 3.75% uncertainty, but I was asked for absolute uncertainty, so now I take the 0.0375 times the 800 to find out what percent that is, and I come up with 30.0. So my absolute uncertainty is plus or minus 30 for this measurement. So to propagate uncertainty, when you add or subtract measurements, the absolute uncertainties can just be added. You never subtract the uncertainty. The uncertainty never gets less. Every time another measurement is brought into the calculations, more uncertainty is added to the calculations. When you multiply and divide measurements, the percent uncertainties should be added. So you're still adding the uncertainty, but now you're adding the percent uncertainty rather than the absolute uncertainty. When you're averaging, however, the uncertainty remains the same, because if you continue to add the uncertainty when you're averaging wouldn't do anything to help your uncertainty. It would simply increase this. But since it's the same, your uncertainty is the same for all like measurements, you can simply leave it the same. The percent uncertainty can just be converted back to an absolute uncertainty.